Hi everyone. Uh, in the last video lecture, we saw that how can we use the Pillman equation in order to estimate the value of a state. Now, I want you to understand that how do we update the value of a state when we have new information about the environment. So, as I told you previously that we are going to, uh, for example, we are in an environment where we have four states S1, S2, S3 and S4, and corresponding to these states we have their corresponding V values. Because we have just started our environment, the estimate and the values of these states are going to be random. We would have randomly initialized V value for them. So for S1 we would have V1, for S2 we would have V2, for S3 we would have V3, and for S4 we would have V4. And as I said, because we have initialized randomly, this v value corresponding to each state is also going to be random. It is only with the passage of time and with more and more training we are going to reach the actual values of each state uh, in the environment. So now we have the Bellman equation, and we know that we initialize the value of each of the state randomly. So we need to update the value of each state so that we can reach the actual value, or if we or because we are trying to find the optimal value for each of these states. With the passage of time we should be able to find the optimal value for each of the states. So what we are trying to do is that, and what I am trying to say is that we need to find the v optimal for this state S. We are trying to find the V optimal for this test, for this state. What is V optimal? V optimal is the value of this state S in the most optimal policy. So as I told you earlier that we are always finding the V value of a state under a policy. The V optimal is the value of this state S under the most optimal policy. So what we are trying to do, we are striving to find the value of this state as under the most optimal policy. This is what we are striving to do. Let me reframe my words. From a randomly initialized v values, we are trying to find the most optimal v value for each of these states. So initially we start with v1, v2, v3, v4, and what we are trying to find, we are trying to find v1 optimal, v2 optimal, v3 optimal, and v4 optimal. Why are we trying to find the optimal values? Because once we have the optimal value for all of the states in our environment, we can say that the policy that we are using in our environment is the most optimal policy. I hope the concept is clear that what we are striving in the environment, we are striving to find the most optimal value for each of the state in my environment. But how do I move to a better estimate of the v value for a state? So if I am randomly initializing, I might start with a value that is 1. With the passage of time, I need to improve the value of this state. I need to find a better value for this state. So it is with the passage of time, it is going to improve, and after so much training, after a certain time has passed, we would be able to reach a value which is going to be its value with the most optimal policy. And that is the whole objective, that is the whole training objective of training a reinforcement learning algorithm. We are striving to find the best value for our states, or if I am talking about state action function, we are trying to find the most optimal value for a state action pair. I hope I am able to convey that in a reinforcement learning what we are trying to do and how do we do it. So for far before I move into how do we actually update the value of a state, I want to do a recap. In reinforcement learning, we have an agent. The agent takes an action, gets a reward R for it, and because it has taken an action, it moves into a state S dash. Now, if I want to find the value of a certain state in my environment, I can use the value action formula and where the value action function. And if I want to find the value of an action, I can use the action value function for it. Then I introduce you to the Bellman equation. The Bellman equation helps us to find the V value or Q value for a given state or state action pair respectively. So this is where we have reached so far. In this lecture I am going to explain to you that how do you update the V value for a given state. And again let me repeat, I am showing you how to update V values. The Q values, that is the action value function, is updated the very same way. Actually, if you would ask me, I am going to create a video in which I will show you that how do these two functions, the state value action and the action value function and the state value function, relate to each other in one single equation. But it is not necessary to understand it for uh, reasoning LLMs. So let me start with the very equation that we are familiar with. This is the standard Bellman equation when we are trying to find the value of a state. We randomly initialized a value s for a value v of s for the state s, and now we need to update it. This equation here represents the most optimal condition for this state s, because look at it. This is basically the estimated best value for this state s. This whole thing in its entirety represents v of s, and this thing is also representing the same thing v of s. If the new estimate of our v of s minus our old estimate of v of s is equal to 0, what does that mean? What does that indicate? It means that we have found the actual value of v of s. We have found the most optimal value of v of s. What I mean by that is that we start from some random value, for example 1, 2, 3, 4, and then after 4 this value has stopped to change. Every time I take the difference of the new value from the previous estimate, I always get 0. So this means that this is indeed the most optimal value of v of s, or you can say the actual value of v of s under the policy pi. So if I am trying to find a value for v of s, but it is not, but it is different than what it was before. So this is the before value of v of s, and this represents the new value of v of s, and the difference of them is not equal to 0, then that means that this v of s can be improved. Now that we know that v of s can be improved, there must be a strategy to improve that v of s, and just that strategy is called temporal difference learning. And this is the formula. This whole thing actually represents how temporal difference learning works. Basically, for each v of s, we try to find the error first. What is the error? This is exactly the same thing. We try to find that is our old estimate different from our current estimate. How do we know that if it is different or not? If it is the same, then the subtraction of them is going to yield 0. But if they are not the same and our new estimate is different from our old estimate, they are not going to be 0 equal to 0. So what we do is that we find the difference, we find the error in our estimates, and then we use this error to update our v value for the given state. If you see it clearly, what we are doing, we have our old value of this state plus there is a learning rate. This is the same learning rate that we use in the deep learning. The concept is exactly the same. We do not want to make huge updates to our state. We do not want to make any update to our state that is going to radically change its value, so we control it via this parameter alpha, which is the learning rate. Coming back to the equation, we have the old estimate of our value plus learning rate times the error that we have calculated using the new estimate. This part represents the new estimate, this part represents the old estimate. The difference of them represents how much is the error. This alpha value controls that how much we update or how much we yeah, it dictates that how much do we update our v value of the given state, so that we do not make a change that is too huge, because we know that if we make a change that is too huge, it might be because of some circumstances that are not normal. Okay, so yeah, let me recap what I've said in this block. What I'm trying to say is that if I have a given state v,